I prepared two application problems that has to do with this new rule that we talked about in this section, which is that the derivative of e to the x is equal to e to the x. So that's the only thing new we learned in this section, and some more fancier versions of that. But let's remember this and solve this application problem. A restaurant purchased kitchen equipment on January 1st, 2017. On January 1st, 2019, the value of the equipment was $14,650. The value after that date was modeled as follows. This is interesting because, usually we make the base year, we make the year we purchased this machine as the base year. So like I would have thought 2017 would be year 0. But no, they're saying that this is the model starting from January 1st of 2019. So we're using 2019 as a base year, because look at the wording here. The value after that date, okay, and that date, they're referring to the 2009 here, was modeled as follows. So when they're asking for the rate of change, okay, and by now we know whenever they ask us to find the rate of change, we need to find the derivative, right? So they want us to find the rate of change in the value of the equipment on 2019. So what I'm going to do is I'm going to find the derivative function and plug in t equals 0, okay? So let's look at this exponential function. What will happen is when we do the chain rule, the derivative of this exponent will come down as that negative 0.158 and get multiplied by that original leading coefficient of 14,650. So get your calculator and type in 14,650 times that negative decimal. When you do that, you will get the new leading coefficient of negative 2,314.7. Okay, now do not change that exponential term. Okay, keep it exactly the same and bring it right down. Now that's the derivative function. So how fast was this value changing in the year 2009? You can figure that out by plugging in t equals 0. So what happened? I'm doing e to the negative 0.158 times 0. But as you can notice that the exponential term has an exponent of 0 now, right? So what is anything to the 0 power? We're just going to get negative 2,314.70 cents, because this is just 1, right? That's just $1 per year. Okay, so in year 2019, the value is depreciating because that value is negative. The value of this equipment is going down by $2,314.70 per year on this date. Okay. Now I start to wonder, how much was this machine when they first bought it back in 2017? Now think about this. If t equals 0 for 2019, we're going back in time, right? For 2017, that's 2 years before 2019. So 2 years before, I'm going to use t equals negative 2 for year 2017. Part B is asking for the original value of this equipment in 2017. And like I said, I'm going to plug in t equals negative 2. They're asking for the original value. They're not asking for the rate of change in value. So we're just going to use that value function they gave us in the beginning, okay? Not the derivative function that we came up with, but this value function, because that v of t gives us how expensive this machine is. So look, we're going to find the price 2 years before this date by plugging in negative 2. So if you were to find the price after 2 years, then we plug in positive 2. But 2017 was 2 years before our base year. So that's why I'm plugging in negative 2, okay? So do 14,650 times e to the negative 0.158 times 2. This whole thing can be typed into your calculator, okay? So you can, I think I will open up a Desmos Scientific calculator. So I'll go Desmos Scientific. And I'll type this in. 1 second. Typing in 14,650 times e to the negative 0.158 times 2. So the original price of this machine was $10,680.72. That's how expensive this thing was when they first bought it in year 2017. All right, so that's it for this problem on page 84. I think there is a similar problem on your homework, so maybe that's why I included this example. But I think this one was interesting because we actually plugged in a negative value to find the original value of this machine.